Welcome to my presentation about unifying metadata-based storage reconstruction and carving with LAYR. As the title indicates, I would like to introduce a forensic reconstruction and analysis framework called LAYR that allows generalizing and combining different reconstruction techniques. As you all may already know, there are many different forms of digital evidence. Digital evidence can, for example, be a video file stored on a hard disk, an email sent over a network, or a password stored in a computer's main memory. No matter what data is involved and how it is stored, storage resources are usually organized through abstraction layers where higher level storage is constructed from lower level storage. Usually, investigators try to acquire digital evidence via low-level access to minimize the dangers of unintentional errors. But the task to reconstruct concrete pieces of high-level evidence from low-level evidence is not trivial since it involves decoding the mapping between the pieces of data and to bridge the semantic gap. For example, the figure shows the different storage abstraction layers which have to be passed through while analyzing an NTFS file system. In NTFS, the master file table must be found and passed to extract file metadata pointing to the starting and ending address of an active file. If the file has been deleted but the metadata is still present in the MFT, then a file might still be reconstructed as long as the sectors have not been reallocated for a different file yet. If no metadata exists at all, files may still be reconstructed through file carving. But why should we take a closer look at this at all? As I said in the beginning of this presentation, there are many different forms of digital evidence. And every form can be stored, parsed, and analyzed in a different way and with different approaches and tools. Because of this variety of technologies, we need a way to generalize and formalize storage abstraction layers and the reconstruction of data. Okay, so let's dive into the model we've created to formalize data reconstruction. Usually, abstraction layers are used to structure software systems, separate concepts, and provide isolation. In the analysis of file systems, Brian Carrier systematized the analysis of data on persistent storage from the physical to the application level. Later on, Freiling, Glanzmann, and Reiser generalized Carrier's model to arbitrary types of block-based storage that is organized as a finite sequence of fixed-size memory blocks. For our framework, we use slightly modified versions of their definitions to create a simplified model, which is the basis for our approach. This figure shows two abstraction layers. Hereby, the type of layer is irrelevant. It could, for example, be a file system and files, a storage device, a partition, but also a database and database entries. Let's have a closer look at the different parts of the model. As you can see in the picture, the different layers are consisting of sequences of blocks. A block is a sequence of bytes of a fixed size, and blocks are identified by an index, which is a natural number. A sequence of blocks is called a storage object. A storage object is a tuple of pairwise distinct block indices. A set of storage objects is called a layer, in this case one lower layer and one upper layer. The relation phi in between captures the rules of how to interpret the lower layer to yield higher layer objects. All these parts together build a level of abstraction. Based on this abstract model, we've created a modular framework to generalize different reconstruction tasks. For the reconstruction of storage objects, we need something which decodes phi. In our framework, we call this a heuristic. Heuristics implement specialized reconstruction tasks like parsing partition tables, file system structures, or carving for files. To combine different heuristics, we defined operators. Operators allow combining different heuristics to perform more complex reconstruction tasks. Operators can be divided into two categories: the sequential operators which work on a vertical level, and the parallel operators which work on the horizontal level. I will now briefly discuss the individual operators before we have a look at a complex expression. The vertical sequential composition operator evaluates a heuristic H1, which is a DOS partition table parsing heuristic, and then evaluates another heuristic H2, which is an X3 file system parsing heuristic on either all or a subset of the results of H1. This allows reconstructing objects across multiple layers of abstractions by chaining different heuristics together. This figure also shows the vertical processing of the chained heuristics very nicely. The symbol on the upper right corner of the red box represents the sequential composition operator and can be used for a more formal expression of the process. A formal representation for this example would be the formula on the right-hand side, and as you can see, H1 and H2 are connected by the sequential composition operator symbol. The vertical OR operator can be used to try out a heuristic on a particular input, and if that fails, try another one. This example shows how the OR operator can be used to handle a partition containing an X file system where the version is unknown. First, an X3 heuristic is applied. Since the actual file system version is X4, the X3 heuristic fails in a controlled fashion and the X4 heuristic is subsequently applied. As on the slide before, the OR operator symbol can be found in the upper right corner of the red box, and I think because the principle is clear, there is no need to mention the expression symbols on each slide. In addition to evaluate one heuristic after the other, it is also possible to evaluate two or more heuristics on the same input and combine their results. The horizontal union operator combines the results of two heuristics by joining them together. This is especially useful if two different techniques should be combined to generate more results, for example. The intersection operator is another parallel operator which returns all storage objects that both heuristics return in their result. Thus, the intersection operator can be used to generate results that create a confidence in the validity of the results. We also implemented a subtraction operator which removes the results of the second heuristic from the results of the first one. This operator can, for example, be used to remove active files from the carving result set by subtracting the file system result set. As I already mentioned, operators can be used to chain several heuristics and combine their results, thereby allowing to build complex nested expressions to deal with complex reconstruction tasks. This is possible because the result of applying an operator to heuristics is yet another heuristic. This example shows the combination of the operators and heuristics I've shown you on the last few slides as a nested expression. By using the operator symbols, this complex expression can easily be expressed formally. The lowest layer represents a storage device which contains two partitions. The partitions are evaluated by the DOS heuristic H1. After the user has chosen a partition, the X3 heuristic H2 is applied. After H2 failed, the X4 heuristic is applied. Afterwards, the carving heuristic H4 is applied and the results of H3 and H4 are joined together by the union operator. To show the practical usability of the framework, we implemented a forensic reconstruction and analysis tool called LAYR, which uses these concepts. The class hierarchy of LAYR was directly derived from the definitions. The modular design and inheritance-based interface of LAYR ensures simple extensibility whereby developers can easily add their own heuristics. And besides, LAYR is written in C++. A major advantage of the framework is that it can easily be converted into code since the interfaces are defined by the model. Furthermore, once phi is identified, phi can also be used to generate decoding instructions for heuristics. To illustrate this, I will now briefly discuss the layer class diagrams. Each heuristic inherits from the abstract parent class heuristic, which has access to the lowest layer represented by the byte container class. This class is an iStream wrapper which provides the possibility to access the lowest layer data stream through a vector-like interface. To realize concrete heuristics, the evaluate function inherited from the abstract heuristic parent has to be implemented. This function implements the decoding of phi and receives a storage object as a sequence of block indices and returns a vector of storage objects as a sequence of block indices. Sequential operators also inherit the abstract parent class heuristic, and therefore the operator functionality is implemented in the evaluate function. The sequential composition operator receives two heuristics and an additional choice function via the constructor, while the OR operator only receives two heuristics. Parallel operators inherit the class parallel, which inherits and extends the heuristic class by adding a set operator function. This function has to be implemented by the child classes union, intersection, and minus. They also receive two heuristics via the constructor. To test how the software architecture performs, we implemented some example heuristic modules, namely DOS and X3, and evaluated them by comparing the results of an invocation of evaluate with the output of the TSK tools MMLS and iStat. For the evaluation, we used two images from the digital forensics tool testing project. In all cases, the invocation of evaluate produced correct results according to the comparison with the generated TSK output. To evaluate the functionality of the operators, we extended the set of heuristic modules by several test heuristics and combined them with the already implemented heuristics by using the operators. We verified the results through a comparison with TSK again, and all test cases produced correct results. For more details about the evaluation, please refer to the paper. To conclude, one minor shortcoming of LAYR is the fact that current heuristics operate on one single storage object as input. While the model and the framework in general are capable to model systems with several input objects, the current LAYR implementation excludes such systems. At the moment, there is no user interface, but it is already planned and prepared that LAYR should understand the formal expressions I showed earlier as input language. Furthermore, the assumption that all blocks at any layer of abstraction are of equal size is not practical, and for simplification, metadata are currently not considered. But the good news is that we are currently working on a new version of the framework where the block size issue is solved and metadata are included. Besides, we are already working on the extension of LAYR, and we are able to integrate third-party software by constructing wrapper classes around their interfaces. For example, we already integrated Scalpel. In the future, we want to model even more complex analysis and reconstruction tasks. Heuristics could also be used to implement complex file filters. These filter heuristics could be used to reduce the amount of reconstruction results to make them more specific to the current investigative question. For example, a black and white heuristic could generate a result set where only scanned documents are included. Another application could be a file name or hate speech heuristic, returning files with specific names or words inside documents, giving a hint of if the content could be of interest. This type of heuristics would then work on the file level and thus again involve a completely new application. But we also thought about adding cloud storage analysis modules or integrating main memory forensics. Okay, so that's it. Thank you very much for listening, and I hope you enjoyed our research.